All right, let's do the sample test, chapter 1. Determine the average velocity between t equal 0.5 and t equal 1.5. And we want to note that this is meters is the unit for that, and the time is in hours. So we want to do 1.5, which is 31.25, 1.5, and 0.5, 25.25, and 0.5. So that's 6 meters divided by 1 hour. So it's 6 meters per hour. Moving pretty slow. And what's the instantaneous velocity at 1? Well, we can't get that exactly, but they say use the central difference theorem, so we're going to go just beyond it. 30.31 minus just before it, 27.31 over 1.25 minus 0.75, which is, let's see, that's 3, difference 3.00, divided by 0.5, which comes out to be 6 meters per hour. And now let's do, to get the S of the slope at 1.75 is this, estimate S of 1.8. So we're going to do our linear approximation at 1.75 because we have information for that. So it's the slope times t minus 1.75 plus S of 1.75, which was 31.81. Then we're going to take and put in 1.8 in for t. So this is going to be 1.8 minus 1.75 is 0.05 times 1.5. 1.5 times 0.05 plus 31.81, and we get 31.885, and we're making an estimate for S, which is this, which is measured in meters. The population of a community is given by this formula, where P is the total number of people and T is the years after 2000. Determine P of 5. So all we have to do is plug 5 into that equation. So let's go to y equals, clear and type in 3000, parenthesis 1.052, close parenthesis to the 2.2 x. Second table, I've got an auto ask in the table set. I've got it on ask in the input. So on the table, I can just type in 5, and it tells me the population would have been 3156 in 2005. And to show my work, here I need to write 3000 parenthesis 1.052 to the 0.2 times 5. Okay, p prime of 30. So now we need to do the estimation of it. So we're going to do the limit as b approaches 30 of p of 30 and a p of, let's see, we go a b, p of b, which is going to be 3000 parenthesis 1.052 to the 0.2 b minus p of a, which we're going to use as 30. So 3000 1.052 to the 0.2 times 30. I better put this in here, b in parentheses, so it doesn't look like 0.26, over b minus 30. And then we're going to use technology here. So I've got the equation in here, and so I'm going to type in parenthesis, 3,000, put the 3 back there, go down here. Numerator, let's just put it in fraction. That's alpha y equal. And then I got to do the numerator, which is y1 of x for my b minus y1 of my 30. So that's just plugging in the 30 and the b into the equation that I have up here, over x minus 30. And then I want to look when x is close to 30. So I'm going to go at 29.99 and 30.01, and I'm getting about 41.2. So I'm getting 41.2. This is all part of B here. And this is the numerator is the number of people, and the denominator was years. So 41.2 people per year is the give the units and tell what this means in this context. So this is the population. And this is, write a sentence, explain the meaning here. The growth of the population per year in, let's see, 2000 plus 30 in 2030. Determine whether p double prime is positive, negative, or 0. Well, this is a growth model, so if I go to just turn this one off and graph on, this is bigger, so zoom fit might do it for me. Oop, what happened here? You can't tell very well here, so I'll go to my window, and minimum is 2,000, max is 4,000. I don't know if you'll be able to see it here. but it's a growth model. It's an exponential curve, so we know that it's curved up. And so the second derivative, the one that says curvature, is positive. And, oops, sorry. Whoa, off the screen there. And you saw, hopefully you saw the graph. It's curving up. Boy, I'm sorry for not showing you that. Determine the equation of the tangent line at P at 30. So that would be L at A equal 30 of the slope. And we found out that that was 41.2 times the population, or T, minus T at 30, plus the population at 30. Do we have that? No, we did the population at 5. So I need to go back to my calculator and find the population at 30. And it says it's 4066.5. Okay. Page 2. Graph the derivative. So we're going to graph the derivative here. So I got to estimate the slope. It looks like a slope of 2 to start off with. So I'm going here, and it looks like 2, maybe 1 in here, through here. So it's going from 2 down to 1, down to 0. 2 to 1 to 0. Looks like it gets to about -1 here. And then it goes back to 0. And then it gets to be about +1, and then it goes towards 0. Gets to +1, and then it goes back towards 0. So I'm just looking at the slopes here. 0, -1, 0, 1, and 0, and maybe a half here. So it should have been about a half in here. It's maybe a little lower, something like that. And then it says to draw the second derivative. So now I need to see this one. To do this, now I'm just graphing the slope of this one. Well, the slope is 0. It goes to negative a half or a third, something like that. And then it goes back to 0 here. And then it goes to maybe almost 1, and then back to 0 by 4. And then it goes to negative small amount. And that's what the second derivative would look like. Now, I could make you go backwards. I could say, okay, now draw the original graph. Well, I'd read the slope as 2, so I'd have to make a graph that has a slope of 2. We wouldn't know where to start, and then it has to go to a slope of 1, and then it has to go to a slope of 0, and then it has to go to a slope of -1, and then to a slope of 0, and then to 1, and then going back to 0. You have to read the y values off of here and make this have those slopes. Okay, so now let's answer the questions. Graph that. Explain what the x-intercepts mean. That means that the slope is 0 up here. Graph f double prime. We did that. Explain what the zeros in the x-intercepts in f double prime mean. That means that when this was 0, the slope of this derivative was 0, and the original graph, slope was 0 here, which means we had an inflection point on the original graph. It was had a slope of 0 here. That's why this was 0. So this has got a slope of 0, which means we're at an inflection point on this graph, changing from curved up to curved down. Explain what the zeros and f double prime about f. Oh, I did both of those. And then besides looking at f, what else is an indication that f is concaved up 0 to 4? It's concaved up, which means the second derivative, which tells us about concavity, is positive. Okay. Use the limit definition in technology to find the derivative of f prime at 3 of this function. So I'm going to go to my calculator, go to the y equal, and change it from that one to 4x sine x, clear all this, 4x sine x, and I need to make sure that I'm in radians. Then I want to make sure that I'm doing this one at 3 and not 30, like I was for the first problem. So now I'm finding at 3, and I want to look close to 3. So I'm going to go to my table again and pick numbers close to 3. 2.999, that's close to 3. And I'm getting negative 11.31. Then I'm going to try just past 3, 3.001. And I'm getting, so it looks like it's about negative 11.3. And I did the limit as b approaches 3 of 4b sine b minus 4 times 3 sine of 3 over b minus 3. And 5. I might be doing these out of order. Did I do these out of order? Nope, 5. Okay. So, as x approaches negative 6, the limit, the left is approaching negative 5, and the right is approaching negative 5, so it's negative 5. As I approach 0, the left approaches 3, and the right approaches 3, so it is 3. Approaches 4 from the plus side. Approaches 4 from the plus side, it approaches negative 3. And as it approaches 4 from both sides, they go to different values, so does not exist because left, and it says, explain why it doesn't exist. Left limit is not equal to the right limit. Use the graph and tell whether it is continuous. At negative 6, to be continuous, it has to have and if not, explain why not. It has to have a limit, it does. Has to have a value, it does not. So not continuous. At negative 3, At -3, it has a limit, it has a value, and they're the same, so it is continuous. At 0, it has a limit, it has a value, but they're not the same. Limit does not equal the value. So, not continuous. And at 4, it doesn't have a limit. So, not continuous. Okay. Using the same graph, and decide whether it's differentiable at -3. Well, to be differentiable at -3, it must be continuous, and it can't be a cusp. Well, at -3, we decided it was continuous, continuous, continuous. So, and it's no cusp. So, it is differentiable because it's continuous and not a cusp.